Okay, so we finished chapter 2 now, and we're going through the chapter 3, which is about the determinant. So at first we will just learn the basic rules and properties of determinant, and later we will see why it is useful. Okay, so let's start with the very basic. So determinant is only defined for square matrices. So square matrix, remember, it means like n times n matrices. Okay, so the number of rows and the number of columns must be equal. So we can only define determinant for such matrices, and we cannot define them for like m times n matrix where m is different from n. Okay, so let's start with the most basic one, which is 2 by 2 case. Okay, when the matrix is 2 by 2, the determinant is simply the product of these diagonal entries minus the off diagonal entries. So a11, a22 minus a12, a21. Okay, let me see if people are waiting. Yeah, people are waiting. Evet, geç kalmayın arkadaşlar derse. Okay, so for example, if we take this simple 2 by 2 matrix, we see the determinant of this matrix is 2 times 5 minus 3 times 4. Okay, so for the 3 by 3 case, the rule is slightly more difficult. So if we take a 3 by 3 matrix, okay, so for the 3 by 3 case, we have this rule here, and it is not easy to remember this rule. Okay, so instead of remembering this, an alternative way is to remember something called the Sarrus Rule, and it works like this. So you write the columns. So this is the first column of the matrix, and the second column, and the third column, and then you repeat only the first and second columns. Okay, so it becomes like a matrix which has 3 rows and 5 columns. Okay, and then the Sarrus rule says this: you look at the first diagonal, you multiply these entries, so you get this term. You multiply these entries and you get this term, and you multiply these entries and you get this term. Okay, and then you subtract terms. Which terms? You first subtract this diagonal. Okay, so which is, wait a minute, which is maybe this one, right? So this one is the same as this one, and then you multiply minus. So people are still joining. Let me admit them. Oh, okay, and then you subtract. So okay, this one is, I think it is this term, and the product of these 3 entries is this one, and the product of these 3 entries is this one. So this is just a visual way to remember this long formula. Okay, so it's hard to remember this, but when you use the Sarrus rule, it is much easier. Okay, and this only works. This Sarrus rule works for 2 by 2 determinants as well. Okay, so if we go back. Where's 2 by 2 case? So if you go back, in fact, Sarrus rule is already working here. You just multiply these entries minus these entries. Okay, so it's kind of Sarrus rule, and this rule does not work for 4 by 4 matrices. So don't try to use it for matrices which are 4 by 4 or 5 by 5. So we can check it, for example, for this one. I think I explained it in YouTube video, so I don't want to go over again. So you write these 3 columns, and then you just use this rule. Okay, so people are still coming. So I think today this Zoom, so this is the free version of Zoom, and the computer science department is trying to buy the license, and without the license, I think we will only we can only use this program for 40 minutes. So after 40 minutes, I think we will just end the meeting and then come back again. Okay, so we will give a break. Okay, this is just for today. Okay, so now we want to define the determinant for general n by n matrices, and this is not very easy. Okay, so it includes so something called the permutation. So what is it? Let's try to understand. So we define a set which is Sn. Sn is simply the set of all integers starting by 1 and going to n. Okay, so 1 to n, and we define a permutation of Sn as a tuple like this, n tuple, which includes each entry only once. Okay, so for example, what does it mean? Let's look at this S2. S2 is the set 1 2, and its permutations are 1 2 and 2 1. Okay, and nothing else. And the permutations of the set S3 are 1 2 2 3 1 3 1 2 1 3 2 3 2 1 2 1 3, all possible combinations. Okay, or all possible permutations. So this is, for example, this is not a permutation. So this is not a permutation for not a permutation of S3. Not a permutation. Okay, so each element must be in this rearrangement. Okay, now next we define something called inversion. Inversion. So if a larger integer comes before a smaller integer, this permutation is called is said to have an inversion. Okay, so we will count the number of inversions. For example, for this permutation of S2, it contains no inversions because 1 is less than 2 and there's no inversion here. But this permutation 2 1 has an inversion because 2 comes before 1. Okay, so it means it has exactly one inversion. Okay, so depending on number of inversions, we call the permutation either even or odd. Okay, so for example, for this permutation, it's an odd inversion. It has on exactly one inversion, so it's an odd permutation. And so we can also look at, so this permutation has no inversions, and this one has two inversions, right? Because 2 comes before 1 and 3 comes before 1. Oh, I'm sorry. And 2 comes before 3, so it will have, wait a minute. So it will have, I'm sorry, it will have two inversions because 2 comes before 1 and 3 comes before 1. Okay, so this ordering is correct. So it will have two inversions. Okay, so we will not use this a lot. So that's why I'm also confusing this. So we won't actually need these things to compute determinants. This is just a theoretical background, how we can define n by n determinants, but we will never use this method to actually compute any determinants at all. Okay, so let's look at this one, 3 1 2. So 3 is greater than 1, so it has one inversion here, right? And 3 is greater than 2, so it has another inversion, and no other inversions, right? So it has exactly two inversions. Any questions here? Okay, so next, what do we do? So another example, let's look at this permutation of S4. So we say it has 4 inversions. Let's see why. So 4 is greater than 1, 4 is greater than 3, 4 is greater than 2. So that gives 3 inversions. And okay, 1 is not greater than anything here. 3 is greater than 2, so it has another inversion. So it will have 4 inversions. So it's an even permutation. Okay. So now let us define a determinant of an n by n matrix. Okay, so the determinant is a sum, okay, of product of elements of the matrix. So what are these products? Well, each product contains exactly n terms of the matrix. And each of these terms come from a different row and a different column. Okay, that's the important part. No two elements in this product comes from the same row or the same column. Okay, so and there's a sign here, plus or minus, and this plus or minus sign is whether these J1, J2, dot, dot, dot, Jn permutation is an even permutation or an odd permutation. Okay. So let's go back to the 2 by 2 case. Okay. So this is the first permutation. So this product contains corresponds to the 1-2 permutation, and this product is 2-1, right? So these are the elements that we are looking 2-1. So you see this one is a even permutation, so it comes with a plus sign, and this one is an odd permutation, so it comes with a negative sign. Okay, and let's look at the 3 by 3 case. Okay, so there are more terms here, but let's quickly check this. So this is 1, 2, 3. So this is an even permutation. It has no inversions. This is 2, 3, 1. So how many inversions does it have? It has 2 inversions, right? Because 2 is greater than 1 and 3 is greater than 1. So it's an even permutation. So it comes with a plus sign. But let's check, for example, this element here. So this element, so I'm looking at 2, 1, and 3. So these terms, how many inversions does it have? So 2 is greater than 1. It has 1 inversion and no other inversions. So it is an odd permutation, so it comes with a negative sign. Okay. Bazıları kopuyor herhalde arkadaşlar. 59'a düştük. Az önce 64'tü. Bağlantı sorunu yaşayan var mı? Herkes duyabiliyor mu? Yani ben burada kendi kendime anlatıyor gibi bir hissiyattayım şu anda. Umuyorum takip edebiliyorsunuz. Chat'ten yazanlar var. Bir saniye. Birkaç arkadaş giremedi hocam. Bir saniye. Merhaba hocam. Evet, evet, evet. Duyuluyor, duyuyoruz. Tamam, sorun yaşamıyoruz. Birkaç arkadaş giremedi. Sorun yok diyorsunuz. Duyuluyor. Okey. Yani sorun yaşayan varsa da nasıl çözeceğim bilemiyorum buradan arkadaşlar. Tamamen benim dışında olan bir sistem bu. Bakalım 40 dakika gelince uyarı verecek mi bize? Okey. Evet, şu chat'i de şöyle açık tutayım arkadaşlar. O zaman bir şey yazarsanız buradan görebilirim. Tamam. Eğer bir sıkıntı olursa gene şey yaparsınız, oradan yazarsınız. Okay, let's go back to the general definition then. Okay, so I think I explained this, right? So I don't want to go over again. So this is the 3 by 3 by 3 determinant. So we explained that these terms are corresponding to the even permutations, and these terms are corresponding to odd permutations, so that they come with a negative sign. Okay. So I just gave 3 exercises from the textbook. You can look at them. So as I said, we will never use this general formula to compute any determinants. Okay, we have much easier ways. We will see them later. Okay. So let's look at the properties of the determinant. Okay, so the first property is determinant of a matrix does not change when you take the transpose. Okay, this is very important. For example, I demonstrated this only for 2 by 2 case. You can check this for 3 by 3 case, and you can also look at the proof in the book. Okay, the proof is also not difficult, it's easy. So for example, if you take the transpose of this, we get this. And let's see if this is equal really. So this is AD minus BC, and this is AD minus BC. So they are same. So we showed this for 2 by 2 case. And next we will look at these elementary row operations and how it affects the determinant. So we had three elementary row operations. Let's look at each of them. The first one is swapping rows. In this case, we see okay, so if we swap two rows, the determinant has a minus sign. There comes a minus sign in front of the determinant. Okay, I also demonstrated this only for 2 by 2 case, but you can look at the general formula. So, so in this case, so if we swap, for example, these two rows and look at the determinants, this is AD minus BC and this is BC minus AD. So they are negative of each other. Okay. This is just a proof for 2 by 2 case, and this result holds for like any n by n matrix. Okay. Okay, and the next thing is if two rows are equal, then the determinant is automatically 0. I mean, if two rows, yeah, if two rows or two columns are equal, then the determinant is automatically 0. So the proof can be done using the previous thing, because we have seen that if I swap rows, the determinant must change sign. But so if two rows are equal, then if I swap them, I get the same determinant, but on the other hand, I will get a negative determinant with a negative sign. So this is a number and this is it's negative. So a number equals is negative means that number must be 0. Okay, no other possibilities. Again, we can see this for 2 by 2 case, AB minus AB, or if you look at this 3 by 3 determinant, then we automatically see that this is equal to this row. So two rows are equal, which means it's automatically 0. No need to use Sarrus rule or anything here, okay? Okay, so any questions? Sorusu olan varsa söylesin arkadaşlar. Ya normal derse göre biraz daha hızlı gidiyoruz galiba, böyle kimseden feedback alamayınca. Okay. So okay, next thing is if a row consists entirely of zeros, then the determinant is 0. So why is it so? Because just remember the determinant sum formula, okay? So as I said, let's go back to the determinant sum formula. So determinant is a sum of products, and each product contains exactly one element from each row, okay? So means every time each of these products will contain a term which is 0. So we're just adding zeros here, which gives 0. So this just comes from the determinant sum formula, okay? And the same thing is holding true for columns as well. So when you see something like this, determinant like this, it is automatically 0. Okay, one thing about the notation. So so if I put like braces, like brackets like this, like vertical lines, this means determinant, okay? So there are people coming. Okay, so when I have this vertical straight lines, it means I'm computing a determinant. So notice the difference between these brackets, okay? So this means matrix. This means matrix. And if I put these lines, this means determinant. Notice the difference. Okay, so next elementary row operation is multiplying a row by a non-zero number and replacing it with that row. Okay. In this case, the determinant is also multiplied by that number. Muhammed Erkam Sancak giremiyor herhalde. Oh, okay. So Bazıları düşüyor galiba sürekli arkadaşlar. Sürekli tekrar kabul ediyorum. Okay, let's look at this 2 by 2 case. So you see we have this ABCD determinant, and you see here the first row is multiplied by the number k. In this case, what do we have? So this determinant is basically k times this determinant, which validates this formula for 2 by 2 case again, okay? So all of these things can be done using this determinant sum formula, okay? So I don't want to go into details because it takes too much time. The formal proofs takes too much time, so I'm just giving you the idea. And the last operation is, so I'm multiplying another row by k, jth row, and adding it to the ith row, and then replacing it with the ith row. Okay, and in this case, the determinant does not change. Okay, again, let's demonstrate it for this very simple case. So what do we have? So we have, if we compute this determinant, we get this. And this is exactly the same determinant, right? Why? Because if we expand this, what do we get? AKB plus AD minus BKA minus BC, right? So these two terms will cancel each other. So we get the same thing. So people usually confuse this elementary operation and they multiply the determinant by k. So don't do this, okay? This is a mistake. So you should be careful about this. When you do this elementary row operation, the determinant does not change. Later we will see how to compute the determinants. We will see a method to compute determinants using these elementary row operations. Okay, it's very handy. Okay, so for example, if I have this determinant and if I do this type of elementary row operation on that matrix, then the determinant won't change. Okay. And this is, wait a minute. So yeah, this is the end of first part, week 5. So I will continue with week 6. Let me know if you have any questions. You can turn on your microphones and ask questions. Ben de bu arada bir şeyi getireyim arkadaşlar. Sorusu olan var mı? Duyabiliyor musunuz? Herkes duyma sorunu yaşayan var mı? Sorun yok diyor Ediz Efe. Herhalde bu dönemi böyle geçireceğiz arkadaşlar. YÖK de açıklama yaptı biliyorsunuz. Bu bahar döneminde yüz yüze ders olmayacağına dair. Evet, bir dakika bekliyorum arkadaşlar. Sorularınız varsa düşünün. Sormak istediğiniz bir şey varsa. Sınavlar hakkında bilgimiz var mı? Sınavlar hakkında hiç bilgim yok arkadaşlar. Biz de bekliyoruz ne olacağını. Bana da mail atıyorsunuz bazen. Ben de herhalde rektörlük bu konuda bilgilendirme yapacaktır. Yani ne yapılacağını bence şu anda kimse bilmiyor nasıl olacağını. Çünkü insanları çağıramıyorsunuz yani sınav olması için. Uzaktan sınav diye bir sistem yok. Bakalım ne olacak bilmiyorum. Muhtemelen yakında çözerler bu sorunu diye düşünüyorum. Yani şu anda siz sadece derslerinizi konsantre olun, ders çalışın. Ondan sonra sınav kısmı bir şekilde hallolacak herhalde. Ya benim tahminim vizeyle finali aynı zamanda muhtemelen olacak. Yani arada bir haftayla falan. Yani eğer bu işler Haziran falan gibi çözümlenmiş olursa önce vize, ondan sonra final şeklinde olacak. Okay, so this is about week 6 and okay, so maybe oh We received a gift from Zoom which says, we removed the 40-minute time limit on your group meeting. Okay. Update geldi. Okay. Okay, so we can continue after 40 minutes. Okay, so this is the second week. So we will continue with the properties of determinant, okay? Bir saniye arkadaşlar, wait a minute. Okay, so we have the next property, which is about the triangular matrices. Okay, we have seen two types of triangular matrices, which are like upper triangular matrix or lower triangular matrix. And for these matrices, it's very easy to compute the determinant. You just simply take the product of the diagonal entries. Okay, let's just check it for this type of triangular matrix. Okay, so this is an upper triangular matrix, 3 by 3 upper triangular matrix, and which means the elements below the diagonal must be 0. So these numbers can be anything, and ABC also can, some of them can be 0, okay? But the important part is the elements below the diagonal must be 0 for an upper triangular matrix. In this case, it's just the product of these 3 entries, and the other terms do not come into play, okay? So how can we see this? We can see this easily using the Sarrus rule, for example, right? I'm sorry, A0, 0. There's a star here, B and 0. And there's a star here, and then C. And we repeat these, we repeat these columns, and then if you use the Sarrus rule, so this will give me like a plus, this will come with a plus sign, this will come with a plus sign, and this will come with a plus sign. Now let me change the color. And these will come with a negative sign, right? But you see, the sign is not important. Only this term contributes because the others are all zeros, okay? So this is also true for lower triangular matrices, and also true for like general n by n matrices, okay? You can easily see this from the determinant formula, okay? Determinant sum formula, because as I said, each term in that formula comes from a different row and a different column. So if you use this idea, from the first row, you can only choose this guy, right? From the first row. But once you choose this guy, you cannot choose this guy because two terms cannot be in the same column. So you must choose another element, but only this element will play a role. And once you choose these two guys, you cannot choose this one or you cannot choose this one. And this is already 0, so you can only choose this term. And this goes on like this. So you cannot choose this one, this one, this one. Must be this term. So you just get this product. Okay, so this is also this this property also holds true for diagonal matrices. So diagonal matrices are those matrices which have zeros above the diagonal and zeros below the diagonal, okay? So a diagonal matrix is a matrix which is both upper triangular and lower triangular. So when you see a matrix like this, you don't need to use any fancy formulas. You just compute this determinant by taking the product of entries on the diagonal. Okay, so what do we do? Okay, for example, if we have the identity matrix, then its determinant must be 1. Okay, so let's look at this example. So this is not in triangular form, okay? So people sometimes confuse this as a triangular matrix, but this is not a triangular matrix. So to be a triangular matrix, as I said, the elements, either elements above this diagonal or below this diagonal, must all be 0, and this is not true for this matrix. So, but instead what we can do is we can swap these two rows. If we do them, we automatically get an triangular matrix. Okay, so this is -1, 0, 0. So I already explained this in the YouTube video, but I'm going to repeat it again. 3, 4, 5. So that you can ask questions and tell me if there's something that you don't understand. So once I do this, once I do row swap, there should be a negative sign here. Okay. And then the determinant is very easy to compute. It's the product of these entries here. Okay, -1, 2, and 5. And there's also another -1 coming, so the answer will be 10. Okay. Okay, so in this slide, we are seeing that since determinant of a matrix and its transpose are same, we can also use the column operations. Okay, so instead of row operations, we can also use column operations, and they work in the same as the row operations. Okay, so everything we said about row operations is also true for column operations. So there's nothing special about rows. Everything holds for columns as well. So for example, if I swap two columns, the determinant changes sign. If I multiply a column by a number, then the determinant is multiplied by the number. And if I do this third type of column operation, the determinant does not change. Okay. So for example, for this example, what is it saying? So we notice that the second column is a multiple of first column. Okay, so in this case, the second column can be made 0 by using this type of elementary column operation. I multiply the first row by -2 and I add it to the second column. And what do I get? Let's see. So if I do this operation, I get 3, 4, -1, and I get 0, 0, 0 here, and 5, 0, 1 here. Okay, so since this column is 0, once a column is 0 or a row is 0 or zeros, then that determinant is automatically 0. Okay, so we talked about this rule, and it's also clear from the determinant sum formula. Any questions? Okay, so let's look at this one. So we can use the Sarrus rule, which I mentioned earlier, or we can try to use elementary row operations to bring this matrix into a triangular form and then compute the determinant. Okay. So how does it work? First, I multiply the first row by 1/2, and if I do that, I know that the determinant must be like multiplied by 1/2. And if I want to make it equal, so I have to multiply this Lie matrix by 2. Okay, so let me write it here. So let's write here 2, 0, 2, and then 4, 1, -3, 6, 2, 1. So this determinant is twice the determinant which has half the first row. Okay, 2, -3, and 1. So these two sides are equal. And next, what do we do? what do we do? Now we try to make this entry 0, right? So this part 0. How do we do that? Well, to do that, I have to multiply the first row by -2 and then add it to the third row and write this instead of third row. And if I do this operation, I know that the determinant will not change, okay? So what do I get? I get, wait a minute, 2 times 1, 2, 3, and 0, 1, 2, and 0. So -2, -7, and -6, -5. Okay, like this. Okay, so this is still not in triangular form. I have to make this entry equal to 0. And to do that, what I do is, what can I do? I can multiply the second row by 7 and add it to the third row and write it instead of third row. So if I do that, what do I get? I will get 2 times 1, 2, 3, and then this doesn't change, 0, 1, 2. And this will become 0, 0, and 2 times 7 is 14, so this is 9. Okay, now this matrix is in triangular form, right? Because this part is all zeros. So this is really like bringing the matrix into row echelon form. This is not row echelon form, but we could also, yeah, this is in row echelon form, right? No, I mean, this, if this was 1, this would be in row echelon form. We can do that. We can multiply the last row by 1 over 9. And okay, let's do that. Let's do that actually. Let me find that place. So we could write this in this way: 2 times 9 times and 1, 0, 0 and 2, 1, 0, and this is 3, 2, 1. Okay. So which operation I'm doing here? I'm multiplying the third row by 1 over 9. So if I do that, I will get 9 times this determinant, okay? So now I know that the determinant is just the product of ones here, which gives me 2 times 9 times 1, which is 18. Okay, any questions? Okay, this somebody is asking what does determinant represent? What does it show? I think we have few of its uses in the next slides. Okay, and I will talk more about its what geometrically determinant means. But let me make a like a small remark here. So, for example, if I want to compute something like this, 1, 2, 3, 4. So what does this show? This is -2, right? So what this shows is, what this represents is, one of the ways to understand determinant is, so you look at, this is a 2 by 2 case, and you look at this column and this column. So 1, 2 is a vector. Its x coordinate is 1 and y coordinate is 2. So this vector. And what is 3, 4? 3, 4, 2, 3, 2. So this is 3, this is 4. Not the best choice, maybe 3, 4. 1, 2, 3, 4. Okay, so this is not very good. Anyway, let me do this 3 by 3, okay? So I didn't like this. So let's make this 3. Or even, so let's make this 1. So what does it give me? It gives me -5, right? -5. So that I can show you on the graph what it means. So 1, 2, and 3, 1. So it is this vector. Okay, so what this determinant gives me is basically the area of this parallelogram. Okay, so it's the main geometric idea is this. So what about this minus sign? Well, it gives me a signed area. Okay, so the sign is chosen according to like how these vectors are oriented. So if I swap these 2 columns, I know that it will become +5. Okay, so 2 by 2 determinant of 2 by 2 matrix is basically the area of the parallelogram obtained by these 2 columns. And the same thing holds true for 3 by 3 determinants. So it's this time volume of the 3 vectors. So if I have 3 vectors, they will form something called parallel pipe. So 3-dimensional thing, and its determinant will be the volume of this parallel pipe. And the same thing holds true for general m by n determinants. Okay, but we will talk about this later. And determinant has, this is not just for this geometrical aspect. It has far-reaching implications. We will see some of them in a few seconds. Okay. So let me try to draw the 3 by 3 case. So if I have this 3-dimensional thing, so it's very difficult to draw, right? How can I draw this? Maybe I don't draw the coordinate axis. So if I have these, so if I have this, I hope it looks like something. So this is one of the, so I get a 3-dimensional object like this. And the determinant will give me the volume of this object, the signed volume. Okay, there will be a sign. Okay, I think let's give a break. Okay, let's give a 10-minute break, and then we will continue. Okay. Görüşürüz teneffüs arkadaşlar. Evet, sorusu olan var mı arkadaşlar? Bazı arkadaşlar resmini bile koymuş buraya. Vallahi bravo. Örümcek adam koyan bir arkadaş var. Bu kimdi ya? Hakkı Bulut mu bu? Kim bu? İsimleri nereden görüyorum acaba? Burak Çağlayan'mış. Ha. Kim bu Burak Çağlayan? Duyuyorsunuz değil mi arkadaşlar? Hakkı Bulut değil mi? Evet, tahmin etmiştim. İkimiz bir fidanın güller açan dalıyız diye bir şarkısı vardır. Biliyor musun onu Burak Çağlayan? İkimiz bir fidanın güller açan dalıyız diye gider. Evet arkadaşlar. Zamanında bizim 45'lik şarkılar diye bir grubumuz vardı. Onunla böyle 70'li yılların şarkılarının, türkülerini falan çalıyorduk. Hakkı Bulut'ta çaldığımız kişilerden bir tanesiydi. Evet arkadaşlar, gördünüz ha. Tamam, süper. Ee, Bir şey diyecektim ya. Arkadaşlar ben bugün bir yanlış yaptım. Yani normalde bizim dersimizin saati 3 değildi. Ben bir şekilde 3 diye hatırladım bu saati. Ee, Ders saatimiz 1'di değil mi arkadaşlar? Yani bir 3'te başka bir ders olabilir. Dolayısıyla biz normal ders saatimizde yapalım. Haftaya ben gene göndereceğim şey saat 1'de. Dersimiz 1'de. Yarın iki dersimiz de saat 4'te olması lazım. 4'te. Ben niyeyse 3 diye hatırladım bir şekilde bakmadan. Dolayısıyla bundan sonraki haftalarda hep normal saatinde yapacağız. Eğer bir değişiklik olmazsa. Tamam. Ee, Evet arkadaşlar. Şimdi şu şeye gelelim bir saniye. Şuraya geleyim. Evet, soru yoksa dersler yüklenecek mi? Evet, yüklenecek. Bu dersi kaydediyoruz şu anda. Umuyorum bir yanlışlık olmuyordur. Bir daha bakalım. Evet. Şu anda kayıt oluyor arkadaşlar. Bu dersi yükleyeceğiz o sisteme. Ama bunları anlattığım şeyler zaten. YouTube videolarında da bunu anlattım. Yani bundan sonra eğer bu sistem başarılı olursa ayrı bir YouTube videosu yapmama gerek olmayacak. Dolayısıyla ben bunu herhalde Zoom üzerinden bu yaptığımız dersi sisteme yükleyeceğim. Öyle düşünüyorum şu anda. Yani öncesinde bir çekim yapıp tekrar yapar mıyım bilmiyorum. Bakacağım. Tamam. Şimdi arkadaşlar, okay, let's continue. Uh, let's recall the elementary matrices, okay, elementary matrices. So we have seen this in the last lectures, elementary matrix. So if I do this elementary row operations on the identity matrix, then the resulting matrix is called an elementary matrix. Okay, so since we have three types of elementary row operations, that gives me three types of elementary matrices. Okay, so let's recall those elementary matrices. For example, let's just do it for the 2 by 2 case. For example, if I have 2 by 2 identity matrix, which is this one. And if I do this row operation on it, row 1 swapped with row 2, then I get 0, 1, and 1, 0. Okay, so this is an elementary, this is called an elementary matrix. Okay, so you see, if I do, okay, so determinant of this matrix is what? Determinant of I2 is 1. And since this matrix is obtained, from I2 by a row swap, its determinant must change sign, okay? So it's 0, minus 1. You see it is minus 1, okay? So when I do a row swap on the identity matrix, I get minus 1. And if I multiply a row by k, then the determinant is multiplied by k. And since the determinant is 1, I get the result k. And I know that this type of elementary row operation does not change the determinant. So this is 1. Okay. Now we will use these to prove some theoretical things about matrices. Okay, so there's a lemma here which says if I have an elementary matrix like this, then and if I compute E times determinant of E times A, then I can separate the determinant into a product, determinant of E times determinant of A. Okay. So okay, so let's look at the proof of this one. So here I'm just taking one of these elementary matrices, okay? So this proof can be repeated for other types of elementary matrices as well. So let's just look at this row swapping elementary matrix. Now, what does it mean to multiply a matrix by an elementary matrix from left? Well, this is simply doing this elementary row operation on A, right? So let's remember it here. So let's just look at this one. So for example, if I take a matrix A, which is A, B, C, D, then if let's call this E. Now what is E times A? So if you remember, if I do this 0, 1, 1, 0 on A, B, C, D, what I get is, okay, 0, 1, so this gets C, this gets D, A, and B. You see, this is just the matrix A where row 1 and row 2 are swapped. So I am expressing, in a sense, these elementary row operations by matrix product, okay? So elementary matrices help me about that. Representing elementary row operations by products, by matrix products. Let's go back. Okay, take the elementary matrix, this one, then E times A is the matrix with row I and row J swapped. So this is what we have seen here. So the determinant here is negative of determinant of A. Why? Because you see this matrix has determinant negative of determinant of A. Okay. So on the other hand, if we compute this, then determinant of E we discussed here, right? So this is minus 1. So this is minus 1 and this is determinant A. So this is minus determinant of A. So you see this equals this in this case for this type of elementary matrix. Now repeat the proof with other types of elementary matrices and you will see that this identity always holds for elementary matrices. Okay. So later we will see in next slides, we will see that this is not true this is not only true for elementary matrices, but this is true for any two matrices, okay? So any two square matrices, determinant of A times B equals determinant of A times determinant of B. Very good. Very good. So next, okay, we're going towards this important theorem, which characterizes all invertible matrices. Okay, so before that, we need to do this technical part. Anything you want to ask? Okay, continue. Soru soracağınız zaman mikrofonu açıp da sorabilirsiniz veya bu yandaki chat'e yazabilirsiniz arkadaşlar. İkisine de bakıyorum. Yani chat'e bakıyorum arada. Okay, so what does this lemma say? So if B is a matrix which is row equivalent to A, then we have this property. Determinant of A is non-zero if and only if determinant B is non-zero. Okay, so this means either both this one and this number are zero, or both of these numbers are non-zero. So it is not possible for one of them to be zero and the other one to be non-zero. This is what this property is saying. How do we see that? Okay, so this proof, the proof of this property depends on the previous things we have seen in the class. Suppose B is row equivalent to A. What does it mean to be row equivalent? Well, row equivalent means B can be obtained from the matrix A by using elementary matrix operations. Okay, so those three type of elementary row operations, you use them and you end up with B. Then you say B is row equivalent to A. And if we know that if B is row equivalent to A is also row equivalent to B, because each elementary row operation can be inverted. Okay. So, okay. Now the last sentence I said, B can be obtained from A by using elementary matrix operations, is the same as saying that B is a product of elementary matrices times A, okay? Because each elementary matrix represents an elementary row operation, okay? So, okay, now let's look at the determinant of B. What is determinant of B? Well, it is this determinant because these two matrices are same. But what is this? Now, if you look at this part, you separate this part and this part. Now, this is a matrix. This part is a matrix, and it is multiplied by an elementary matrix, which by the previous property, I can separate it into two determinants like this. Okay? Determinant of EK times this guy. Now I can repeat this for EK minus 1, EK minus 2, dot, dot, dot, and E1. Okay? So at the end, I get this result. So what does this give me? So if you remember, let's go back to the previous slide. These are the elementary matrices. So none of them can be zero. Okay? So this K is not allowed to be zero. So K is non-zero here. Oops. So none of them can be zero. So none of these determinants are zero, which means this matrix, if it is zero, then this should be zero. And if this is non-zero, this should be non-zero. Okay, that's what we wanted to prove. Okay, now comes the important thing. So the question is, which matrices have an inverse? Okay, so this theorem, this is a theorem, by the way. Let me write theorem. This theorem fully characterizes all the matrices which have an inverse. So a matrix has an inverse, or it is called non-singular, if and only if its determinant is non-zero. Okay, so this is just like real numbers and multiplication. So if you think about real numbers, which real number does not have an inverse with respect to multiplication? So for example, 2 have an inverse, which is 1 over 2. So if I multiply 2 and 1 over 2, I get the identity 1/2. Okay. So, okay. The only real number which does not have an inverse is 0. Okay, 0 does not have an inverse. Same thing for the matrices. The only matrices that do not have an inverse are those matrices whose determinant is 0. All the others have an inverse. Okay. So this is a very important property. It saves a lot of time sometimes. So for example, if you come up with a question whether a given matrix has an inverse, you just check its determinant. If it's 0, then no. If its determinant is non-zero, the answer is yes. So how does the proof go? The proof goes like this. So if A is non-singular, then we know that it's a product of elementary matrices. Hence, its determinant is non-zero. Because I know that I can separate product of elementary matrices and like a determinant of product of elementary matrices, and it must be non-zero. On the other hand, if A is singular, we have seen some time ago that A is row equivalent to a matrix B, which has a row of zeros. So, but a matrix whose which has a row of zeros has determinant 0. Okay, we talked about this. So its determinant must be 0. Okay, so the important thing is not the proof. Okay, you can maybe forget about the proof, but this is the important part. So only those matrices which have non-zero determinant have an inverse. Let me know if you have questions. Okay. Now we have a corollary to the previous thing. So let's look at this equation, which is called an homogeneous equation because the right-hand side is 0. So A is a square matrix. A times x equals 0 has a non-trivial solution if and only if its determinant is 0. Okay. So what does this mean? For example, let me give some examples here. Let me give some examples. Let's look at the 2 by 2 case. For example, suppose x1 plus x2 equals 0 and 2x1 plus x2 equals 0. So this is an equation of this type of ax equals 0, right? This is the 2 by 2 case. So the question is this: does this system of linear equations have a non-trivial solution, or does this system have only the trivial solution, which is the 0, 0? Okay. So first note that 0, 0 is always a solution. Is always a solution. So this solution is called the trivial solution. Okay, so why trivial? Because we did not spend any time. Because if you put 0, everything is 0. Trivial means bodies, right? So this is the bodies solution. Okay, so does this system have any other solutions? Well, the answer just depends on check its determinant. If it is non-zero, the trivial solution is the only one. So this is 1 minus 2. This is minus 1. This is not 0. So the answer is the trivial solution is the only solution. The trivial solution is the only solution. Okay. So this system does not have any other solutions except the trivial solution. So the equations could be more complicated. So we could look at a 3 by 3 example, for example, x1, x2, x3 equals 0, and then x1 plus 2x2 equals 0, and finally, let me give this one. So the question is whether this system of equations have a non-trivial solution, or does this system only have the 0, 0, 0, the trivial solution? Well, just check its determinant. Just check its determinant. So if its determinant is non-zero, then the trivial solution is the only solution you will get. So just check this one. So if you check this one, you see this third row is a multiple of the first row, which means if I multiply the first row by -2 and add it to the third row, I get exactly this, which is 0. Because a determinant which has a row of zeros must be 0, okay? So now in this case, what do we say? Yes, this system has a non-trivial solution. Yes, this system has a non-trivial solution. Any questions about this? Görüntüm açık mı arkadaşlar? Ben görüntümü açmayı olabilir miyim? Tamam. Sorusu olan var mı arkadaşlar bu yazdıklarımla ilgili? Anlaşılmayan bir yer var mı? So a couple of remarks. So what I said is only true for square matrices here, okay? Because we can compute the determinant only for square matrices. So that's important. And you see, this is very powerful. So instead of like searching for solutions, you can immediately answer one specific question, whether the system has only the trivial solution, so which means you don't look for the other solutions in that case, or it has other solutions. So just look at the determinant. If determinant is not 0, then there are no other solutions, okay? Because if the determinant is non-zero, then that means this matrix has an inverse. This A matrix has an inverse, okay? So if A has an inverse, if the determinant is non-zero, A has an inverse, then I can just write this one, A minus A inverse times AX equals A inverse times 0. But this is the 0 vector. Any matrix times the 0 vector makes it 0 vector. And this part is the identity. Identity matrix times X gives me only X. So I get only the trivial solution if the matrix A has an inverse, okay? That's very important. So I don't need to go over this. So if the determinant is non-zero, then A inverse must exist. And if inverse exists, I know that this equation, the homogeneous equation, has only the trivial solution. And also, if inverse exists, we know that it's reduced row echelon form. We talked about this before. RREF of A must be identity. So when does this hold? This holds when A has an inverse. If A has an inverse. Okay. Can the linear system have more than one solution? No, because it has an inverse. If it has an inverse, we only get one solution, and that solution is the trivial solution in this case. Okay, let's look at this result now. If I have two matrices, two square matrices, if I take their products and then take the determinant, now I can separate this into a product of two determinants. Okay. And since this is true for two matrices, it also holds true for any number of products. So if I have A, B, C, then I can separate this. First, I separate this part and this part, right? And then I separate these two because I know the formula is holding. So this gives me determinant of A, determinant of B, and determinant of C. So I can separate any number of matrices when I'm taking determinant like this, okay? Product of determinants. So the proof, how does the proof work? So the proof works like this. So if A is non-singular, so it doesn't say anything about non-singular matrix here, but let's suppose first case A is non-singular, and then we work with the case where A is singular, okay? If A is non-singular, then I know that it's a product of elementary matrices, okay? So this is this result we have seen several classes ago, and so determinant of A times B is A can be represented by this product times B, and I know that I can separate determinant of elementary matrices like this. We have seen this in the previous slides. Okay, so here now. Okay, so at the end, I get this part equal to determinant of A and times determinant of B. Okay, so this is what we had to prove. Why this is determinant, why this is equals determinant of A? Because we have seen this property holds for elementary matrices. Okay. And the second case, when A is singular. When A is singular, A is row equivalent to a matrix which has a row of zeros. We have used this in the previous slide as well, somewhere here. Yes, right here. So we have used this second time today. So it means what? So it means since A is a product of some elementary matrices times the matrix C, then I can separate this part, and this is the remaining part. But now determinant of C times B, what is this determinant? Now if C has a row of zeros, just let's look at this 2 by 2 case. So suppose this is C, and I multiply it with any matrix here. What do I get? Now, if I do this, in the second row, I will get zero. I will get this row times this column, which gives me a 0 here, and this row and this column, which gives me a 0 here. Okay, so at the end, we see the second row must be 0. And if one of the rows is all zeros, then its determinant must be 0. So in particular, this guy must be 0. And if this part is 0, what did we prove? Okay, so this is 0. what am I trying to prove? Okay, so if this is 0, right? So this guy is 0. What about the other part? What about this part? Now determinant A must also be 0 because we said that it's singular. So in the previous slide, we have seen that if it's singular, then its determinant must be 0. And that's what we wanted to prove. Good? Any questions? Okay. So let's look at this example. If I have the matrix A, whose determinant is 5, and the determinant of the matrix B is -3, then determinant of A times B is -15, okay? And determinant of A squared is 5 squared, which is 25. So also, what did we see here? So if A and B are non-singular, which means if A and B have an inverse, then so is A times B, okay? If determinant of A is non-zero and determinant of B is non-zero, then determinant of A times B is non-zero, which means if A has an inverse and B has an inverse, then AB has an inverse. We have already seen this, right? Because AB inverse is what? AB inverse is B inverse times A inverse. And this also answers the following. If one of these guys does not have an inverse, if either A or B doesn't have an inverse, then A times B cannot have an inverse because determinant of AB is zero now. If one of these guys has determinant zero, determinant of this one is also zero, which means this matrix is not invertible. Okay, so this is that. Now, let's talk about the determinant of the inverse matrix. Okay, so we know that identity matrix is equal to the matrix A times its inverse if A is invertible. And now I can write determinant of I equals determinant of A times A inverse. And I can separate this. So from the previous result, I know that this equals this. Now, what is determinant of I? So this is just 1, which means determinant of the inverse is 1 over determinant of A. Okay, so this is the proof of this corollary. So this is good. So one last reminder maybe, or like warning. So we can separate the determinant of product, but not the determinant of sum. Okay, so if I have two matrices A and B, their determinant is not the same as determinant of A plus determinant of B. So in the YouTube video, I have given an example about this. So you can just take like any kind of matrix. Like in general, this will not hold true. So if you add these things, 1, 0, 5, minus 1. And if you look at the determinant of the result, it won't be the same, right? So what is this matrix? This is 2, 2, 8, 3. Now what is determinant of this guy? Its determinant is 4 minus 6, which is minus 2. What about this? This is minus 1. What about this? 6 minus 16, which is minus 10. Okay. So you see minus 2 plus minus 1 is not the same as minus 10. Okay. So we have to be careful about this one. So here I have listed some exercises for you to look at. So you can look at these things and tomorrow we will have the class at 4, right? So if you have any problems about these, you can ask me. Let's see, yeah. I think that's the end of it. So we still have some time, so we can chat a little bit. So if you have questions or anything you have in mind, you can tell me. Sorusu olan varsa konuşabilir arkadaşlar. Ya bir şeyler söylemek isteyen. Zamanımız var şu anda. Evet, nasıl buldunuz? Biraz görüşlerinizi alayım. Takip zor mu oluyor? Ne diyorsunuz? Teknik sıkıntı yaşayan var mı? Neden saatiniz sadece 9.41'i gösteriyor diyor. Neden öyle oluyor? Ben de anlayamadım onu arkadaşlar. Niye öyle oldu? Burada normal gösteriyor. Yani burada niye 9.41'i gösteriyor? Bunu anlayamadım. Benim de dikkatimi çekti. Evet, 10 üzerinden 10 vermiş Mustafa Can Türker. Tekrar izleyeceğim demiş. Apple lansmanlarına gönderme mi? Ne demek o? 9.41'de mi başlıyor onların şeyleri? Siz kendiniz mikrofonunuzu açıp konuşabiliyor musunuz arkadaşlar? Konuşabiliyorsunuz değil mi? Böyle bir hakkınız var. Ben buradan herhalde isteyeni açabiliyorum. Mesela Burak Çağlayan'ı bir açayım. Burak orada mısın?
Ses.
Evet, geliyor sesin. Tamam Burak'cığım, sağ ol. Seni kapatıyorum tekrar. Var mı söylemek istediğin bir şey Burak?
Yok hocam, sağ olun.
Tamam. Arada böyle kontrol edeyim. Belki açıp giden vardır. Evet. Ben bir isim daha seçeyim. Muhammed Eren Ünlü. Burada mısın? Duyuyor musun?
Evet, buradayım.
Tamam. Tamam. Seni de kapatıyorum. Tamam. Evet, yani uzaktan eğitim başka nasıl kullanabiliriz bilmiyorum arkadaşlar. Önerileriniz varsa söyleyin. Sonuçta hepimiz yeni öğreniyoruz. Böyle bir şey ilk kez başımıza geliyor. Kamera açabiliyor muyuz? Açabiliyor musunuz? Kamera açabiliyor muyum? Galiba kameranızı açamıyorum arkadaşlar. Yani sorabiliyorum. Mesela birisine soralım. Barış Hazar. Mesela Barış Hazar'a ask to start video diyelim. Bilmiyorum ne diyecek. Sonra başlatacağım demiş. Başka birine soruyorum. Dahan'a soralım mesela. Görebiliyor muyuz? Dahan Öztürk. O da sonra başlatacağım dedi. Birisi parmak falan kaldırıyor. El çırpanlar var burada. Sancar Han. Ben bu el kaldırmalarınızı genelde görebiliyor muyum bilmiyorum arkadaşlar. Yani participants da var. Ha, mesela Barış Azar el kaldırdı. Elini indir diyebiliyorum. O elini indir. Tamam. Ha, buradan geliyor mesajlar. Birileri elini kaldırıyor arkadaşlar. Tamam, yani bu imkanlarınız var. Bence kullanın. Bugün kimse şey yapmadı. Bir soru falan sormadı arkadaşlar. Biraz daha çok sorarsanız bak bayağı iki derslik şeyi daha hızlı bir zamanda bitirdim yani. Alt tab atını görebiliyor musunuz? Ne demek o alt tab atını? Şey demek mi? Başka bir uygulamaya geçen mi? Ben Mac kullandığım için bende Command Tab var. Tamam. Alt tab atını görebiliyorum arkadaşlar. Alt tab atmayın. Hangi şu anda uygulamaya baktığınızı görüyorum. Oyun oynayanları biliyorum şu anda. US Marmara'yı kullanacak mısınız? US Marmara'yı arkadaşlar bunun videosunu yüklemeye çalışacağım şimdi şeyden sonra. Kayıt olacak. Oradan bakabilirsiniz. Yani bu videonun kaydını alıyorum ben şu anda. Bunu sisteme yükleyeceğiz arkadaşlar. Yani şu anda bu dersleri yapıyoruz. Umarım sınavda yapabiliriz. Yani öyle yani bu dersi güzel bir şekilde tamamlarız diye düşünüyorum arkadaşlar. Düşüncelerim bunlar. Yani bol bol zamanınız olacağını düşünüyorum. Bol bol lineer cebir çalışın. Lineer cebir önemli bir ders. Yani bilgisayar mühendisliğinin yani software'lerin bir sürüsünde kullanılan temel bir fikir aslında bu. Yani buraya size biraz örnek yazmaya çalıştım. O örneklerden bakabilirsiniz. Yarın ders olacak mı? Yarın ders olacak arkadaşlar. Acaba merak ediyorum, yarınki ders için ayrı bir şey göndermem gerekiyor mu size, yoksa gene buraya hep beraber bağlanabilecek miyiz? Ondan emin değilim arkadaşlar. Belki yarınki ders için ekstra bir şey yapmamız gerekecek. Sizin kayıt almanız sıkıntı yaratmaz ama gerek de yok. Niye gerek yok? Çünkü zaten yükleyeceğim. Oradan da indirebilirsiniz. Veya istiyorsanız kendinize kayıt alabilirsiniz. Sıkıntı yaratır mı? Yani şeyi bilemiyorum. Hani burada başkaları da belki konuşacak. Onlar açısından sıkıntı yaratabilir. Yani benim açımdan bir sıkıntı yaratmaz. O yüzden ben kayıt almanızı önermiyorum arkadaşlar. Sizin hesap premium'a geçti. Ya belki tekrar açabilirsiniz. Benim hesabım premium'a geçtiğini zannetmiyorum. Bugün muhtemelen Zoom bize iyilik yaptı gibi geliyor bana. Yani kullanmamız için programı herhalde bir şey verdiler diye tahmin ediyorum. İlk dersi özel olabilir. Bence de öyle. Yani bugün böyle yaptılar. Yarın 40 dakikada kısıtlayabilirler. Bakalım artık. Bunun şeyi ne kadar çok pahalı değilse belki de anlayabilir yani lisansı. Acaba sadece ben mi alıyorum, yoksa hem ben alıyorum hem siz mi alıyorsunuz? Yani size bir para olmaması lazım tabii ki. Eğer sadece ben alıyorsam belki ben kendi paramla da alabilirim. Bakmam lazım fiyatı ne kadar diye. Ne kadar hakikaten bu Zoom? Hmm. Herkes 1 lira verse. Zoom'un premium'u ne kadarmış bilmiyorum ki. Bakalım bir Zoom premium. Plans and pricing. Aylık 15 dolar 100 katılımcı için. 15 dolar aylık yazıyor. Yani alınmayacak bir şey değil arkadaşlar. Sonuçta yani mecbur kalınınca yapılacak bir şey. Bizim gerçi dersimizde 100 kişiden fazla kayıtlı var ama 100'den fazla insanın da geleceğini zannetmiyorum. Ben bugün 65'e kadar çıktık. Şu anda 50'lere düşmüş zaten. Tahminim 100 kişilik, 100 katılımcılık şeyin yetmesi lazım. 15 dolar diyor. Yani dolar da biraz arttı gerçi ama bir seferlik alınabilir. Bunu bir tek ben alıyorum ama galiba. Değil mi? Herkesin vermesine gerek yok böyle bir şey diye tahmin ediyorum. Katılımcı için. Katılımcı için. Ne demek katılımcı için? Herkes için mi yani? Herkes mi 100 dolar verecek? Twitch mi kullanayım? Yani herkes 15 dolar veriyorsa çok fazla para. 100, aylık 1500 dolar ediyor. Aynı anda 100 öğrenci katılabiliyor. Bir kişi veriyor hocam. Tamam. Bir kişi. Okey. Twitch, Twitch, Twitch, Twitch'te nasıl oluyor arkadaşlar? Twitch'e geçsek diyor. Valla yani bilgisayar mühendisliği bölümü bu şekilde uygun gördü. Dolayısıyla böyle yapıyoruz. Donate atarız. Sağ olun arkadaşlar. Donate'e ihtiyacım yok. O iPad'den işe boş verin. Evet, yorumlarınıza bakıyorum şöyle. Evet arkadaşlar. Çok değişik bir şey yoksa bugünlük burada bitirmeyi düşünüyorum dersi. Hearthstone oynarız. Oynarız arkadaşlar. Hem isteyen de katılır. Evet, akşam da Hearthstone yayını yapmayı düşünüyorum. Twitch'ten. Oraya da gelebilirsiniz. Evet, Yasin Tarakçı çıkmış. Onu da alalım tekrar. Evet arkadaşlar, sorusu olan var mı lineer cebirle ilgili? Yani bugünkü dersimiz biraz teorikti. Bunların uygulamalarını falan daha sonra yapacağız arkadaşlar. Buraya kadar anlattığım materyal zaten YouTube videosunda falan da koymuştum. Dediğim gibi hepsini bugün kayıtta şimdi dersten sonra yüklemeye çalışacağım. Sistemi yüklemeye çalışacağım. Oradan tekrar bakabilirsiniz. Ya bence kendiniz kayıt bilmiyorum yani ne fark eder. Sonuçta oraya ekleyince oradan da indirebileceksiniz. İstiyorsanız alın diye düşünüyorum arkadaşlar. Bugünlük burada bitirelim isterseniz. Konuşmak istediğiniz bir şey yoksa. Nesrin is asking, sir, are you going to send us PDF of the lesson before we have it? I'm not sure about it. So you can of course always follow. I have the full lecture notes, right? So in my website, I have the full lecture notes, and the PDF files that I shared, those slides are just the slide format of the same thing. So you can always read it before. So I suggest, like in general, I suggest you study before coming to class. That makes a huge difference for your understanding. So if you're exposed it the first time, so you try to figure out what's going on. But if you read it before, then you really know what your questions are, and I think it's better. I'm not sure if I will send you the PDF before, so I don't know if it's useful for you. You can always, I don't know. You suggest. Should I send you? Do you want the PDF before? Yes, please. Okay. So I will try to. I'm not sure. Okay, I will try to. So those because changing the format takes a lot of time. So to take the lecture notes into the slide format, it's really takes too much time. But I will try to. Yeah, why not? Okay. Okay, guys. I will see you tomorrow. Thank you for coming today.